Aisha, that's not a very good thing to do. ये तो बहुत ही गलत बात है वैसे। वैसे जस्ट अ पीस ऑफ एडवाइस, जब आप आगे जाएंगे यूनिवर्सिटी में ना, बहुत सारे लोग इस तरह कह रहे होते हैं कि दे टेक सम वर्क ऑफर्स लाइक दिस। सो ये होता है कि आपने किसी बच्चे की असाइनमेंट करनी है, उसके आपको वो पे करेंगे। प्लीज डोंट डू एनीथिंग लाइक दैट, इट्स वेरी अनएथिकल। it's not something that any of you should be involved in. बात करने में वो इतना जो है वो बुरा नहीं लगता, लेकिन अगर आप इसको रियली बाकी सोचें, आप जो है वो you're deceiving someone, should not do that. प्लीज इस तरह के काम किसी नहीं करने पाए आगे जाके, किसी की भी असाइनमेंट किसी भी तरह करें। या भाई ऐसे ही होते हैं, भाई जो है ना वो बहुत तंग करते हैं भाई। मुझे अपने बेटे को देख के ना मुझे हो रहा होता है कि बेचारी जो है वो कितना तंग करता है उसको, अपनी बहन को। अच्छा, let's see. This is working. सारे वैसे मूड ही खराब किया बस पेपर ने, तो आज दिल भी नहीं करा भी करने को। Yes, Serena, I'll do that because I just thought कि वो कल M1 workshop भी है, तो I'll share that link as well there. So yes, I will be doing that. M1 on Wednesday, Clarence, how many classes have we left? 2 classes, yeah. Don't let them do that ना। अगर अब हो गया है तो बस अब आपको, मतलब हम भी कोशिश करेंगे और आप लोग भी कोशिश करें कि they don't do what they did last time. They don't do what they did last time. तो ये बहुत जरूरी है। Expected grade, we should not be accepting expected grades at all. They have to come up with some alternative. या तो अभी retake करें if they have to do a retake. Yes, तो we will all support that, of course. अभी हम teachers भी आपस में discuss करते हैं, and we'll have to do something about it. अभी तो कुछ नहीं कह सकते कि क्या होगा. We can't say anything what is going to happen. But one thing is clear that it's everywhere now. So कुछ ना कुछ तो अब इस पे एक्शन होगा. अब वो क्या एक्शन होगा? Let's hope it's not like last year जहाँ पे लोगों को expected grades मिल गए थे और फिर उनको उन्होंने ऑफर कर दिया था कि अक्टूबर नवंबर में आप दे सकते हैं अगर आप देना चाहें विदाउट एनी चार्जेस. That's not going to help. अब अगर तो ये कंफर्म हो जाता है कि हुआ है लीक तो फिर we need to make sure that we don't let them do what they did last time. कि एक्सपेक्टेड दे दें अक्टूबर नवंबर में ले जाएं अक्टूबर नवंबर में आपके सारे यूनिवर्सिटी एडमिशन्स खराब हो जाते हैं. सो या मेरे सोचने से कुछ नहीं होगा. आई डोंट हैव द एविडेंस फॉर दैट तो उस पर तो कुछ नहीं कर सकता. मैं कुछ कह नहीं सकता. आई कांट से एनीथिंग अबाउट दैट बट लेट्स hope something good comes out of it inshallah. Abhi ke liye we're going to be doing this but uh, I'm thinking of discussing with the other math teachers and also with the admin of how to go about it. But we need to do something about this. अब तो ये हर जगह पे है. As I said earlier, my initial reaction was that we should not say much because के ना ही कैम्ब्रिज तक बात पहुंचे और इसी तरह अगर बहुत माइनर लीक था तो उससे कुछ ना हो और आपके जो है अगर माइनर लीक था तो इसी तरह से हो जाए और आपका पेपर अच्छा हो गया ज़्यादातर लोगों का तो उसी के बेसिस पर आपका ग्रेड आ जाए. बट अब तो इट्स एवरीवेयर. सो समथिंग नीड्स टू बी डन कि जो भी होता है कि नेक्स्ट जो लास्ट ईयर हुआ था उस तरह नहीं हो कि वो एक्सपेक्टेड ग्रेड दे दें और वो अक्टूबर नवंबर में आपको रीटेक की ऑफर कर दें. दैट्स नॉट गोइंग टू हेल्प. अगर आप सिर्फ M1 की बेसिस पर आपका ग्रेड आ जाए तो उसका वो बहुत अनलाइकली कि आपका ग्रेड अच्छा हो क्योंकि M1 आप देख रहे हैं अगर नॉर्मली होता भी है कि P1 P3 में से एक आसान आते हैं तो अब P1 अगर आसान आए तो बहुत लाइकली है कि P3 थोड़ा मुश्किल होगा और M1 S1 में से एक आसान होता है नॉर्मली एक मुश्किल होता है थोड़ा सा. तो उनमें से भी आपके दो मुश्किल पेपर्स एक तरह से रह जाएंगे इसके बाद. तो उसकी बेसिस पर आपको ये P1 के एक आसान पेपर का ग्रेड एक्सपेक्टेड ग्रेड लगाना. लास्ट ईयर इसकी वजह से बहुत मसला हुआ था. लॉट ऑफ पीपल their grades were not very good because of that. So let's see what happens. Let's put some pressure on Cambridge. आप लोग भी करेंगे और हम भी कुछ करने की कोशिश करते हैं इंशाल्लाह. Hopefully something good will come out of it. At least what happened last year, we can't let that happen again. But regardless of that, for now we need to focus on the rest of the papers. आपने M1 अच्छा करना है, S1 अच्छा करना है, P3 अच्छा करना है. ये तो आपने करना है in any case, right? So let's focus on that now. We spent a lot of time discussing this now. This is the paper that we're doing today, November 2021, paper 4-2. This is the M1 paper that I think has the lowest threshold for an A in the last 5-10 years at least that I have seen. उससे पहले भी इतना low threshold जो है I don't think I have seen in any paper. So let's do this. November 21, paper 4, variant 2. Let's do this. Let's start with this. So it says the diagram shows a velocity time graph which models the motion of a car. The graph consists of 6 straight line segments. The car accelerates from rest to a speed of 20 meters per second over a period of 5 seconds and then travels at the speed for a further 20 seconds. अच्छा देखें 5 seconds में ये इसकी स्पीड जा रही है 20 meters per second पे. And then what happens is it travels at a constant speed, constant velocity for the next 20 seconds. The car then decelerates to a speed of 6 meters per second over a period of 5 seconds. The speed is maintained for a further t minus 30 seconds. The car then accelerates again to a speed of 20 meters per second over a period of 50 minus t seconds. Okay. Before decelerating to rest over a period of 10 seconds. So you can see that in the graph, all of that is happening there. Now what we need to do is we need to find, given that during the two stages of motion, when the car is accelerating, the accelerations are equal, find the value for t. Now, how do you do that? The two regions when the car is accelerating, what are those two regions? One is this region where the speed is going up, and the other is this region, again, when the speed is going up. The acceleration is the same. Acceleration is the same in both of these regions. Acceleration is the gradient of the graph, right? So gradient is equal for both of these regions, okay? So we can just equate their gradients. Let's mark this point. What's this point going to be? This is 20 and 50, 50 and 20, that's the point. And the other one, this is t and 6, all right? And the first part, that's origin. And then this is 520. Their gradients have to be equal. Let's find their gradients and equate them. So we have 20 minus 6 divided by 50 minus t, that equals 20 minus 0 divided by 5 minus 0. And that will give you the value for t. Cross multiply, you get 14 times 5, that is 70. That equals 20 times 50, that's 1000, minus 20 times t. What's the value of t that we get from this? $46.5. Okay, this is 46.5. That's what we were looking for. This number is 46.5. Okay, so now that we've found this number, now they're saying, find the total distance traveled by the car during the motion. Total distance traveled. This is the velocity time graph. How do you find distance traveled in a velocity time graph? That's the area under the graph, right? Area under the graph. Let's find the area under this graph. How can we do that? Let's break it into different parts. How can we make it more efficient? Let's think about it. Okay, so this is one way of doing this. We could say we have this rectangle. You can see how many parts that would become. This rectangle, that trapezium, and then that trapezium. That will be too many shapes. Okay, let's do it another way. We could say, let's find the area of this trapezium. Okay, let's break it like this. Find the area of this trapezium, this yellow one. Okay. And then that's too many shapes that we have to add. How do you make it more efficient? Okay, anyway, let's do it this way, and then we can see if we can make it slightly more efficient if that's possible. Oh, this actually might be so one idea is that we find this area. Okay, find this area, find this trapezium, find this trapezium, find this rectangle, find this trapezium, and find this triangle. That's only 2 marks, a lot of work for 2 marks, but a more efficient way that you can think about here is you could say, in order to find the area under the graph, let's find the area of this bigger trapezium. So let me show what I mean by that. Let's find the area of this. Find the area of all of this. That will make it more efficient. This yellow region, let's find all of this. And then subtract from that the area of this trapezium and the area of this triangle. Right? That will make it much more efficient. Let's do that. Area of the yellow trapezium, let's find that. What would that be? Half into sum of parallel sides. What are parallel sides? The base is 60 plus the side on top. That's going from 0 to 50. This is 50. 60 plus 50 into height. Height is 20. Subtract from that areas of those two figures that I've highlighted in orange there. The triangle, what's the area of that triangle? Half into base into height. We can consider this side as the base. That is 5 units. Then the height is this, that's 20. So that will be half into 5 into 20 minus area of this trapezium. What would that be? From 30 to 46.5, this is 16.5. And then from 25 to 50, this length is 25. So what's that going to be? 1/2 into 25 plus 16.5 multiplied by the height from 6 to 20, that is 14. And that should give us the result. You can see what that is. That will be the area of this. What do we get? What's the answer that we get from this? 759.5. Oh yes, that too. So you're actually right. You're right. We could actually make it even more efficient than this. I'll tell you how, but you're right about that. 759.5. So we could actually make it even shorter by not considering this left side as well, the triangle as well. Just find the area of this trapezium. Yeah, you're right. We could do this. Find the area of this trapezium, and then you just have to subtract the area of this middle trapezium from that. So you would not have to subtract the triangle in that case. That's right. So that will make it even more efficient. Let me do that. I'll just edit it slightly. Area of that yellow trapezium. In that case, the other parallel side, that is going to become from 5 to 50, that will be 45. So it becomes 60 plus 45. Then we could just ignore that triangle. So from that yellow trapezium, just subtract that other small trapezium and you'll get that area directly. That's 759.5. Is that what you're getting? Can somebody confirm this as well? I've got one answer saying this, one saying something else. What do you get from this? Okay, all right. That's fine. Part B, that's what we had to do here. This is the final answer. Let's move on. Question number 2. It says a van of mass 3,600 kilograms is towing a trailer of mass 1,200 kilograms along a straight horizontal road. Okay, one note is very annoying sometimes. I think today's that day. A van of mass 3,600 kilograms is towing a trailer of mass 1,200 kilograms along a straight horizontal road using a light horizontal rope. The resistance forces of 700 Newton on the van and 300 Newton on the trailer. The driving force exerted by the van is 2,500 Newton. Find the tension in the rope. Now, how do you think about that? You can say it's a straight horizontal road, so that might look like this. Let's draw that. We have a van of mass 3,600 kg. Let's represent that here. This is the van. It's towing a trailer of mass 1,200 kilograms. This is the trailer along a straight road using a light horizontal rope. Okay. There are resistance forces of 700 Newton on the van. So assuming that we're going on the right direction, in the right direction, because the van is ahead, we can say the resistance on the van is going to act in this direction. That's 700 Newton. Resistance on the trailer, that's going to act in this direction. That is 300 Newton. The driving force by the van, that is 2,500 Newton. So the forward force here is 2,500 Newton. Find the tension in the rope. What are the remaining forces that we've not represented here? We've got tension on the trailer, that will be acting in the forward direction, away from the trailer. Tension on the van, that will be in the backward direction, again, away from the van. All right, these are the tensions that we get. Now, do we have any other forces? Do we have any other forces? We've got reaction, we've got weight, but they're not going to affect the motion in any way, right? Because our motion is in the horizontal direction. So we can just apply Newton's second law of motion on this and see what that gives us. Let's apply Newton's second law of motion on both of them separately. Let's consider the trailer and the van. Use Newton's second law of motion. Resultant force equals mass into acceleration. What's the forward force? If you're going in the right direction, forward force for trailer is T. Backward force is 300. That should equal mass of the trailer, which is 1,200 times acceleration. That's one equation that we get. And similarly, for the van, we can say the forward force is 2,500 Newton. Subtract from that T and also subtract 700. And that should equal mass of the van, which is 3,600 times acceleration. We've got these two equations, solve them simultaneously, and that is going to give you the result. You can see what that turns out to be. From the first equation, you can say, let's make, do we need acceleration later on? No. So we just have to find tension. What I can do is I can make acceleration the subject. If I do that from the first equation, that will give me T over 1,200 minus 300 over 1200, that will be 1 over 4. Put that in the other equation and see what that gives us. It becomes 2500 minus t over 1200 minus 1 over 4 minus 700. I'm sorry, we had to put that in place of a. What am I doing there? 2500 minus t minus 700, that equals 3600 times t over 1200 minus 1 over 4. Let's simplify this and see what that gives us. 2500 minus 700, that's 1800 minus t, that is equal to 3600 over 1200, that's 3. 3600 over 4, that is 900. And that will give us the value for t. 4t equals 2700. What's the value of t that we get from this? What's the value of t that we get? 675? Okay, 675 Newton. That's the value of tension that we were looking for. Thank you. That's our final answer. Let's move on. Now it says the driving force is now removed and the van driver applies a braking force which acts only on the van. The resistance forces remain unchanged. Find the least possible value of the braking force which will cause the rope to become slack. Which will cause the rope to become slack. How do we think about this? Let's represent all the forces acting in this case now. What are the forces that we have acting? Let me draw that diagram here again. You will be drawing your diagrams with a pencil in the exam so that if you're done with something in the first part, you want to edit that, you can just, erase that and, change that value. You would not have enough time to draw diagrams again and again, okay? So make sure that you do it with a pencil and then you just edit that. Now, what do we get from this? Driving force gets removed and they're saying there's a braking force that's applying now. Where does braking force act? Braking force is going to stop it from moving. If it was moving to the right side, the braking force is going to act towards the left. We can say there's a braking force acting towards the left side as well. That's another force that we've got. Okay. Again, we can use Newton's second law of motion in both of them to understand what the acceleration is going to look like. This is trailer and this is van. For the trailer, what's the forward force? The forward force is T, the backward force is 300. That equals mass into acceleration, just like before. And we get this equation for the trailer. It's the same equation as before. For the van, there's no forward force. There's no forward force. If there's no forward force, it becomes 0 or minus T minus 700 minus B. That equals mass, which is 3600 times the acceleration. Now, they are saying find the least possible value of the braking force which will cause the rope to become slack. Now, what happens when the rope becomes slack? B represents the braking force, yes. B represents the braking force. Now, when the string becomes slack, what happens because of that? When the rope becomes slack? Tension becomes 0, right? There's no tension in that case, which we have a lot of today. But in this case, there's no tension. When it becomes slack, the tension becomes 0. So we put T equal to 0 here. And we put T equal to 0 here. What do we get from that? At the point when tension becomes 0, what's the acceleration going to be? 0 minus 300, that equals 1200 times A. And that will give us the value for acceleration. What's that? That's minus 1 over 4 or minus 0.25. That's the acceleration at that point, right? Now put that here in the other equation. And that gives us minus 0, minus 700, minus B. That equals 3600 times acceleration, which is minus 0.25. And that will give us some value for the braking force. That's 200 Newton. So when the braking force becomes 200, the van is going to slow down so much that the trailer is going to have more acceleration and van is going to have less acceleration, because of which the string will become slack. The distance between them is going to become smaller. So the string is going to become slack because of that. So what's the least value of V that we get for this? That's 200 Newton. If it was more than 200, it will still become slack. But when it becomes 200, at that point, that's the first point when the string becomes slack. Okay, that's what we were looking for in this part. Let's move on now. Question number 3, it says the diagram shows a semicircular track ABC of radius 1.8 meters, which is fixed in a vertical plane. Now, whenever you have an inclined surface like this, do not use constant acceleration formulas. Do not use constant acceleration formulas. Because acceleration is a vector quantity. Acceleration is a vector quantity. Since it's a vector quantity, the direction is changing at every single point here. Acceleration cannot be constant. So do not use constant acceleration formulas whenever you have uh, a curved surface like this, a curved surface like this. I think I said inclined earlier, not inclined, curved surface like this. Okay. All right. Now, we have this semicircular track. It has radius 1.8 meters. That's given. A and C are at the same horizontal level. B is at the bottom. AB is smooth. Okay, so this part of the surface is smooth, and the other part is rough. BC is rough. A small block is released from rest at A. Show that the speed of the block at B is 6 meters per second. Whenever you have curved surfaces, use work energy principle. Do it using the energy method. Okay, do it using energy method. Do not use constant acceleration formulas. How do you use the energy method here? We know from A to B, the surface is smooth. If the surface is smooth, that means there's no resistance, and also there is no driving force. Apart from the weight, the block was just released from A. There's no forward force except the weight component acting on this. So there's no driving force, there's no resistance. When there's no driving force and no resistance, we can also use conservation of energy in that case. Since there's no driving force and there's no resistance, because of that, we can say that the total energy at the point A, that means kinetic energy at the point A plus the potential energy at the point A, that should equal kinetic energy at the point B plus the potential energy at the point B. If any of them was not zero, then we would use the work energy principle. Work done by driving force that equals change in kinetic energy plus the change in potential energy plus work done against resistance. That's a general rule that would work in this case as well. You can also use that here. But in this case, since there's no driving force and no resistance, it becomes simpler if you use conservation of energy directly. So that's what we can do here. We can just use conservation of energy. Now, let's consider this the ground level, the point B. Now, we know the height at the point A, that's 1.8. And the speed was 0. It was released from rest. So there's no kinetic energy. That's 0. Potential energy, mgh, mass is what? Do we know the mass? No, we don't know the mass. Okay, so let's just call that m. Into g, that is 10. Into height, that is 1.8. That should equal kinetic energy at the point B. We have to find that. We don't know what that value is. Let's call that velocity v. Then the kinetic energy would be half mv squared plus the potential energy at the point B, that is 0. And that gives you the value for V. You can see what that turns out to be, because M and M, they get cancelled. 18 into 2, that's 36. And the value V will turn out to be 6 from this. That's what we were looking for. That's the first one. So the speed of the block at the point B is 6 meters per second. Now it says the block comes to instantaneous rest for the first time at a height of 1.2 meters above the level of B. So what happens now is, when the block reaches the point B, it will continue to the right side. And then they're saying it comes to rest at some point, such that that point, when it comes to rest, that point is 1.2 meters above the level of B. This is 1.2 meters, vertical distance. The work done against resistance is 4.5 joules. Now that should remind you about something. Work done against resistance. Whenever they talk about work done against resistance, that should remind you of the work energy principle. What's the work energy principle? Work done by driving force equals change in kinetic energy plus the change in potential energy plus work done against resistance. That's what we can use here. We can say work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus the work done against resistance. What's the work done by the driving force? There's no driving force. It was only moving because of its weight. That's zero. Change in kinetic energy. What about that? At the bottom, we know that the velocity now is 6. And then it becomes, so let's call this point something, let's call this point x. At the point x, this velocity becomes, the velocity becomes 0. Okay. So we know the final velocity, we know the initial velocity. What's the change in kinetic energy? Half into m into v squared minus u squared, 0 squared minus 6 squared, plus the change in potential energy, m into g into h. What's the height? In change in height, that's 1.2. It's increasing. We write 1.2 here. Plus work done against resistance, that's 4.5, and that will give you the value for m. Simplify this and see what that gives you. Minus 18m from here plus 12m plus 4.5. That equals 0. And that becomes 6m equals 4.5. And the value of m turns out to be 4.5 over 6, which is what? 0.75? 3 over 4, yeah, 0.75. That's the value of m that we get. That's what we were looking for. Mass is 0.75 kilograms. Make sense? Any issues with this? No problems? Okay, let's move on. Now it says, a cyclist starts from rest at a point A and travels along a straight road. So until now, this question was easy. This was the second part. You had to think about what would happen when the string becomes slack, that the tension is going to be equal to 0. But apart from that, it was kind of okay. The first question, it required a lot of working for the second part if you did it directly, as in you found the areas individually. But if you do it like this, subtract from the bigger trapezium, the smaller trapezium, that becomes simpler as well. So until now, we've not seen a very difficult question. Let's see what's coming ahead. Question number 4, it says, a cyclist starts from rest at a point A and travels along a straight road AB, coming to rest at B. Okay, so it starts from rest and it comes to rest again at the point B. The displacement at time t after the start is s meters. So we've got this displacement function. So that distance AB is equal to 250 meters. Now we know that it started from rest and it ended at rest as well. Can we find those time instances? So it starts from 0, of course, but what's the time when it comes to rest again? Rest means velocity is equal to 0. We've got the displacement function. How do you go from displacement function to velocity function? You differentiate it, right? So that's what you do. You find the derivative of this and see what that turns out to be. The displacement function is 0.004 into 75 t squared minus t cubed. That's the displacement function. Find the derivative of this. What does that turn out to be? 0.004 is a constant that remains as it is. Derivative of 75 t squared, that's 150 times t minus 3t squared. That's what we get from this. Let's simplify this. 150 into 0.004. That's 3 over 5 or 0.6 t minus 3 into this. That is 0.012. This is the velocity function. Now we need to figure out the time instant when the velocity becomes 0 again. How do you do that? You put v equal to 0 in this. And that gives you 0 equal to 0.60 minus 0.012 t squared. Take t common, and that leaves you with 0.6 minus 0.012 times t equals 0. T is either equal to 0 or 0.6 minus 0.012 t. That is equal to 0. That gives you another value of t. You can see what that is. What's the value of t that we get? 50. Okay, so t turns out to be 50 here. So that means it started from t equal to 0. And at that point, when it came to rest again, it was when time was equal to 50. So it goes from time 0 to time 50. Now we need to show that the displacement from 0 to 50 is 250 meters. We've got the displacement function. All we have to do is input the value of t as 50 there. You can use limits if you want from 0 to 50. However, in this case, since it started from the point A, we know that initial displacement was 0. So we can just input the value of t as 50 in that displacement function, and that will give us that displacement value for t equals 50 there. That gives you 0.004 into 75 times 50 squared minus 50 cubed. And that will give you the displacement value. You can see what that turns out to be. 250. Yeah, so that's the result that we get. That's what we were looking for. Okay, let's move on. That was the first part. Now it says find the maximum velocity of the cyclist. Maximum velocity. How do you find maximum value of any function? You find the derivative of that, put that equal to 0. Right? That's the first go-to method that you have for this. This is a quadratic function, 0.60 minus 0.012 t squared. That's the velocity function that we've got. If we want to find the maximum value of this velocity, what we can do is we can find the derivative of this, put that equal to 0. Let's do that. dv over dt and see what that turns out to be. That's 0.6 minus 0.024 times t. Put that equal to 0 because we're looking for the maximum point, turning point. Turning point is when the derivative is equal to 0. All right, so we have 0.6 minus 0.024 times t. That gives us a value of t. What's that? What's the value of t that we get? 25? Okay, thank you. This is 25. So the maximum velocity is when the value of t is 25. Let's do that. Let's input this value there now to find that corresponding velocity. V equals 0.6 into 25 minus 0.012 into 25 squared, and that will give it the value. What's this value? 7.5 meters per second. That's the velocity that we were looking for. This is the maximum value for velocity. How do we know it's a maximum? Because it's a quadratic function. It's a quadratic function, and the coefficient of the square term, you can see that's negative. So it's going to be an n-shaped curve like this. And we have found the maximum point of that. The turning point is the maximum point for this function. This is what we have found there. All right, let's move on. That was part B. And that's it. That was question number 4, another fairly easy one. Let's look at question number 5 now. It says, a railway engine of mass 75,000 kilograms is moving up a straight hill inclined at an angle alpha to the horizontal where sine alpha is equal to 0.01. The engine is traveling at a constant speed of 30 meters per second, constant speed of 30 meters per second, and it's working at 960 kilowatt. There's a constant force resisting the motion of the engine. Find that resistance force. Mass is given. It's moving up a straight hill. Sine alpha is 0.01 and it's traveling at constant speed. I would recommend always draw diagrams for mechanics questions that they make it easier to understand what the question is saying. We've got this inclined surface. The angle of inclination is alpha. And the mass, the engine is moving up the hill. So let's represent that here. It's going in the upwards direction. This is the direction of motion up the hill. What's the weight of this? Weight is going to act vertically downwards. That is 75,000. Should we do it using forces? Or since we have power given, I think it's going to be easier to do it using work energy method. Although for that as well, we might need to use resultant force equals mass into acceleration. Okay, so let me actually write it down. So we have power information, right? Power is equal to driving force into velocity. Now, power, what is power equal to? 960,000. Be careful about the unit. This is kilowatt. So it becomes 960,000 watt. That equals driving force into velocity. Driving force into velocity, it's moving at 30 meters per second. So we get the driving force from this. The driving force is equal to 96,000 divided by 3, what's that? 32,000, right? So we get the driving force from this, 32,000 Newton. That's the driving force value. Now we are looking for resistance for that's a force as well. Let's represent all the forces acting on this now. What are the forces acting? There is weight of the object. That's going to be 750,000 Newton. We have 3 zeros here. We multiply that by 10 and we get 5 zeros, 4 zeros there, 750,000 Newton. That's the weight. What other forces do we have? It's moving up the hill, so there will be some driving force, and we know the value for that now. The driving force is 32,000 Newton. There is some resistance that they're saying. We have to find the value for that. Let's call that R. This is resistance that acts in this direction. There will be normal reaction, yes. There will be a weight component acting in this direction. But since we are not considering any friction here as such, we can just ignore them as well, right? There's no friction that's involved. We would not need reaction for anything, so I'm just not representing that here just to reduce the clutter. Let's resolve 750,000 Newton here. There are going to be two components of this weight, one in this direction, the other in this direction. If this angle is alpha, then this angle here is also going to be alpha, and then this component becomes 750,000 into sine of alpha. The component of weight along the surface always has sine with it. Okay. And the component of weight perpendicular to the surface that has cos with it. We don't need that. I'm just going to ignore that. These are the forces that we've got acting along the surface. We have driving force acting in the forward direction, resistance acting in the backwards direction, 750,000 sine alpha acting in the backward direction. We can say resultant force equals mass into acceleration. What's the forward force? The forward force is driving force. Backward forces are R. That's the resistance that we have to figure out. Minus 750,000 into sine of alpha. That should equal mass, which is 75,000. Into acceleration. What's the acceleration? Acceleration is 0 because it's constant speed. So the right side is going to be 0 here. And from this, now we can say, let's find the value of R because we know the driving force. The driving force is 32,000. Then we have minus R minus 750,000 into sine of alpha, which is 0.01. That equals 0. You could also think of it this way, since it's constant speed, forward force and backward force, they're going to be equal to each other. You could also do it that way. Okay. That would also work. What do we get from this? What's the value for resistance? What's the value of resistance that we get? 24,500. Thank you. That's what we were looking for. 24,500. Okay, that's resistance. Any issues with this? Any problems with this? No? Let's move on. That was part A. Now it says the engine comes to a section of track, which is horizontal. So now it's going in the horizontal direction. At the start of the section, the engine is traveling at 30 meters per second. Okay, so we've got this horizontal section at the start. Let's say it's here. It's traveling at 30 meters per second. Let's assume it's going towards the right side like this. This is the start. Power of the engine is now reduced to 900 kilowatt. Power is 900,000 watt. Okay. The resistance to motion is no longer constant, so we cannot use constant acceleration formulas, right? Acceleration is only constant when all the forces acting on an object are constant. In this case, they're saying resistance is not constant. So acceleration is also not going to be constant. Okay. So don't use any constant acceleration formulas. It says, but in the next 60 seconds, the work done against resistance to motion is this. Okay. Work done against resistance, that is this. That's also what we're given. And it takes 60 seconds. What we need to find out is find the speed of the engine at the end of 60 seconds. Let's say it reaches here. What's the speed at that point? Now we've got time given and we've got power given. Does that remind you of something? That's the other power formula that has time in it. Power equals work done over time. We can use that to find the work done by the driving force. We've got time given. Time is 60. So we can use this formula to figure out the work done by the driving force. Why do we need that? Because we're going to use that formula. Work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance, right? We'll use the work energy principle to find whatever is missing here. The final speed is missing. So we can find the work done by driving force using this formula. How will that work? P is 900,000. That should equal work done over 60. What's the work done value that we get from this? 60 times 900,000. What's that value? Be careful about the number of zeros here. That can make you do careless errors. Oh, okay, so how many zeros do we have there? 6, okay. 54 million. I would recommend always use commas there like this, or have gaps between every 3 zeros so that it becomes easier to count them and reduces your careless errors. This is the work done by the driving force. Now we've got the work done by the driving force. We can input that here. That's 54 million. That should equal change in kinetic energy. We want to find the final speed of the engine. Let's call that speed V. Change in kinetic energy, it's half into M. M is, do we know M? 75,000. 1 over 2 into 75,000 times V squared minus 30 squared. That's the change in kinetic energy plus the change in potential energy. We're moving on a horizontal track. On a horizontal track, potential energy does not change because there's no change in height as such. That's going to be 0. Work done against resistance, we're given that that value is 46,500. And we can find the value of V from this. All right, you can do that. Find the value of V from this and see what that turns out to be. You'll do some working here. Okay, you'll do this working. And then write down the final answer after that. What do we get? 33.2. All right, so you're getting V equal to 33.2 meters per second there, and that's your final answer. Any problems with this? Is this all right? No questions? Let's move on. That was question number 5. Okay, we've got 6, we've got 7. Okay, that's it. Let's have a look at this now. Now, if you remember, we've done this question in the crash course as well. This is a standard question that I teach now, but this was the first paper in which something like this came. It's not a difficult paper until now, but at the time this paper came, there was no question in past papers that looked like this. Now we've done this when we covered the concepts now, but this was the first time when something like this appeared. So this was a difficult question. I think the next one is that kinematics with momentum thing that's always complicated. Okay, let's have a look at this. It says a block of mass 5 kilograms is held in equilibrium near a vertical wall by 2 light strings and a horizontal force of magnitude x Newton, as shown in the diagram. The 2 strings are both inclined at 6 degrees to the vertical. Given that x is equal to 100, find the tension in the lower string. Now, what are the forces acting on this block? We've got x Newton acting towards the right side. We've got weight of this block that acts vertically downwards. That's 50 Newton. We've got the 2 tensions. Tension acts away from the point of reference. So tension is going to act in this direction. That's 1 tension. And these are 2 different strings. So the tensions are going to be different as well. This is the other tension, T2. All right, these are 2 tensions that we've got acting. These are all the forces on this block. Let's resolve them. Since it's equilibrium, they're saying the forces are in equilibrium. And we are given in the first part that x is equal to 100. Find the tension in the lower string. So we are looking for the value for T2. Now, what do we do for this? Let's resolve the forces. Let's resolve tension. There's T1 and there's T2. For T1, we can say there's one component on the left side, one component vertically upwards. If this angle is 60, we know that this angle is also going to be 60 degrees. So the component that is adjacent to the angle that has cos with it, and the other one has sine with it, this is going to be T1 sine 60. These are the 2 components that we've got for T1. And for T2 then, this is T2. If this angle is 60 degrees, then this angle is also going to be 60 degrees. The component that is adjacent to the angle, that's this one, that's going to have cos with it. So it becomes T2 cos 60, and the component on the other side of the angle, that is going to have sine with it. That's T2 sine of 60. All right, now we've resolved the forces. Just equate the opposite forces now. X should equal T1 sine 60 plus T2 sine 60. And T1 cos 60 should equal T2 cos 60 plus 50. So we equate the forces acting towards the left side to the forces acting towards the right side. They give us one equation. Let's see what that turns out to be. T1 sine 60 plus T2 sine 60. That equals X. Now sine 60, that is under root 3 over 2. So that becomes under root 3 over 2 T1 plus under root 3 over 2 T2 equals X. The value for X in the first part they're saying is 100. That's one equation that we've got. I can just multiply the whole equation by 2 to simplify things. So get rid of the fraction, and that will give me under root 3T1 plus under root 3T2. That equals 200. Okay, so that's one equation that I have. Then equate the vertical forces. Vertically, in the upwards direction, we've got T1 cos 60. In the downward direction, we have 50 plus T2 cos 60. Now cos 60 is 1 over 2, so it becomes 1 over 2 T1. That equals 50 plus 1 over 2 T2. Multiply the whole equation by 2 to simplify things, and that will give us T1 equal to 50. No, 50 times 2. That will be 100 plus T2. This is another equation that we've got. Now we are looking for the tension in the lower strength. That means we're looking for T2. So we can eliminate T1. We have T1 as the subject in the second equation, put that in the first equation, and that will give us under root 3 times 100 plus T2 plus under root 3 plus under root 3 times T2 equals 200. Solve this equation and see what that gives you. This is under root 3 T2 100 times under root 3 plus under root 3 T2 plus under root 3 T2. That equals 200, and that will become 2 under root 3 T2 equals 200 minus 100 under root 3, and that will give the value for T2. You can see what that turns out to be. What do we get from this? 7.74. So that's the value that we've got, 7.74 Newton. That's the tension in the lower strength that we were looking for. Okay. Any issues with this? Any problems, anyone? No problems? Okay, now let's look at the next part. In the next part, it says, find the least value of x for which the block remains in equilibrium in the position shown. Okay, least value of x, that's what we're looking for. Now, in the first part, they said x is equal to 100. That's no longer relevant because now they're saying find the value for x, right? So we can't use the same value. That's just given. We have to find the least value of x for which the block remains in equilibrium in the same position. Now, how do we do that? Let's think about this. What I'll do is I'll just copy this diagram here. So we have that in front while we do the second part. Okay, so this is the situation that we've got. They're saying we've got this force acting towards the right side. Okay, we've got this force acting towards the right side. What's the least value of x? The least value of x for which the block remains in equilibrium in the position shown. What's the least value for x? Now, how do we think about this? Now, think about it. This is x that's acting towards the right side. If x becomes too big, if the value for x becomes too large, what would happen? If x becomes too large, sorry, not too large, they're looking for least value. If x becomes too small, because we're looking for the minimum value, right? If x becomes very small, then we would not have enough force to be able to support this block in its current position. Because of the weight of the block, it is going to start going downwards, right? So if x was very small, so if let's say x was 0, if there was no force acting towards the right side, if this force was not there anymore, would the block be able to remain in its current position? It would not, because it would start moving downwards because there's no force acting towards the right side. It'll start moving downwards. It'll fall down. Now, when that happens, when it starts falling down, what happens to the lower string? What happens to the lower string? The lower string becomes slack, right? So think about it. When that block comes in this position, it comes somewhere here. Now the upper string goes like this. The distance between this end of the string and this, it becomes smaller now. String is longer. It no longer remains taut. It's no longer straight. It's going to become slack, right? So just when the block is about to move in this direction, just when the block is about to move in this direction, what happens is the lower string becomes slack. When it becomes slack, what happens to this tension? This tension becomes 0. That's the point that we're talking about. That is going to give us that value for x. We've got the same equations that we had in the first part. The forces are all the same. It's just that the value of x is now not 100 anymore. It's something else. So what I can do is I can just use that same working again here. I'll copy that here as well. This is the working that we did in the first part. We equated the opposite forces. This is still equilibrium. The opposite forces are still going to be equal to each other. In place of 100 here, we still have x. These are the two equations that we've got. Now, when x becomes very small, and the block is about to move down, what would happen would be lower string. This is just for your notes. You're not going to write all of that in your exam. This is just for your own understanding. The lower string will become slack. The lower string, that is going to become slack. When the lower string becomes slack, that means its tension is going to become 0. Okay. So what we do is we put T2 equal to 0 in both of these equations. Put T2 equal to 0 here. Put T2 equal to 0 here. What do we get from the second equation? We get T1 equal to 100 plus 0. T1 turns out to be 100. Put that value there as well. And you would get under root 3 over 2 times T1, which is 100, plus 0, that equals x. So x equals 50 under root 3. That's the least value of x that you've got. You can find the value in decimals if you want, or just leave it as it is. What's the value in decimals? That's 86.6 Newton. That's the value of x that we were looking for. Okay, so that's the idea. Whenever you have a problem like this, so we generalized this as well when we talked about it. M1, where was that? This is M1. Forces in equilibrium. For finding greatest or least values of any forces, when the object is hanging from some strings like that, what we do is we consider putting one of the tensions equal to zero, because when we're looking for the greatest force of greatest value of a force, least value of a force, such that the block remains in its current equilibrium state, when it's just about to break, when the equilibrium state is just about to break, one of the strings is going to become slack. One of the strings is going to become slack. When one of the strings becomes slack, tension in that string is going to become zero. Okay, that's what we do. Similar questions when you have a rough surface involved that has friction. In that case, we consider limiting equilibrium, right? When the equilibrium is just about to break in case of friction, that's the concept of limiting equilibrium. In that case, we would say the object is just about to move in one direction. Okay, it's just about to move in another direction. It's just about to move in one direction. We consider limiting equilibrium F equals mu r. Okay. All right. Now let's go back to that question. We've already talked about the leak in the start of the stream. That's what we spent some time on in the beginning. So I'm not going to do that again right now. Yes, when it comes for the first time, when it came for the first time, it was not very obvious, right? So now we have done this while we were covering the concepts, but in that time we did not used to teach this concept as well because it was not there in past papers anywhere. But then they gave this, and students had to think about this in the exam itself. So yeah, that's the idea. All right. So when the equilibrium breaks, the string will just about to the block will be just about to move in the downward direction, and the lower string will become slack because of that. All right. Okay, that's the idea. That's this question. Let's move on to the next one now. That's question number 7. We have already talked about the P1 leak. For now, we're focusing on our next components. Let's do this. Question number 7. Let's have a look at this. Particles P and Q have masses m kilograms and 2m kilogram respectively. The particles are initially held at rest 6.4 meters apart on the same line of rate of slope of a rough plane, inclined at an angle of alpha to the horizontal. Okay, where sine alpha is given. So we've got all of this information given. Let's highlight this. The distance is 6.4 meters. That's shown on the diagram. P is released from rest. Simultaneously, that means at the same time, Q is projected up the same line of slope at a speed of 10 meters per second. The coefficient of friction is 0.6. Show that the acceleration of Q up the plane is minus 11.6 meters per second square. Okay, now how do we think about this? Q is projected up the plane in this direction. What are the forces acting on Q? We've got weight of Q. What would that be? 2m times 10, that becomes 20 times m, right? We've got normal reaction that acts in this direction. We've got friction. If it was projected up the plane, where is friction going to act? Friction is going to oppose that in this direction. That's going to be the direction of friction. What else? Now it was just projected upwards. There's no force that is still acting on that. There's no force that's still acting on that in the upwards direction. It was just projected and it was released then. Okay, so there's no upward force as such. Is that it? Do we have any other force acting? We've considered friction, weight, normal reaction. Yeah, that's it. Let's resolve these forces. Weight, what are the components of weight going to be? If this is 20m, then we have one component acting in this direction and the other component acting in this direction. If this angle is alpha, we know that this angle is also going to be alpha, right? So this component is 20m into sine of alpha, and the other one is going to be 20m into cos of alpha. Equate the opposite forces. in the perpendicular direction, these forces are going to be equal to each other. R is going to be equal to 20 m cos alpha because there's no movement. There's no movement perpendicular to the surface. Okay. Now, R equals 20 m into cos of alpha. These should be equal to each other. Okay. So R is equal to 20 m cos alpha. Now, since it was projected in the upwards direction, in this direction, that's the forward direction. What's the forward force? There's no forward force acting in this direction. In this case, what's the backward force? Friction and also 20 m sine alpha. That should equal mass, which is 2m times acceleration. And we have to find the value of acceleration here. How do we do that? Since the object is moving, friction is going to be at its maximum value. So mu times r minus 20 m into sine of alpha. Sine alpha is given to be 0.8. Let's input that value here. That equals 2m times a. Now, what is mu? Mu is 0.6. R is 20 m cos alpha. Do we know the value for cos alpha? No, we can find that. If sine alpha is 0.8, just put this on your calculator and you get the value for cos alpha. I think that's going to be 0.6 most likely. Abdul Hadi, as Aisha said, when you throw a ball in the upwards direction, it keeps moving up even when you release it, right? Do you go yourself with the ball to make it move upwards? You don't. You just release it and it keeps going up for a while. Although after you've released it, there's no force acting on that ball. So it's very similar to that. It's very similar to that. You have projected it in the upwards direction. After you've projected it, it just keeps moving up for a while, right? Because of that initial speed it already has. So there's no driving force on it. There was just some initial force, and then there's no force acting in the forward direction after that. It's just moving because of that initial speed, initial push that was given to it. Okay, minus 0.6 into 20 m into cos of alpha. Cos alpha, let's actually figure that out. Sine alpha is this. So cos of sine inverse of 0.8. That's 0.6. So cos alpha is 0.6. Let's input that here. 20 m into 0.6. That's mu times r. And then minus 20 into 0.8, that will be 16 times m. On the other side, we've got 2m times a. Now, m can be cancelled because that's appearing in every single term. We can divide the whole thing by m. So m gets eliminated. What are we left with? What are we left with? 20 into 0.6 into 0.6, that is 7.2. So minus 7.2 here, minus 16, that equals 2 times a. And that's going to give you the value for a. You can see what that is, 23.2 divided by 2. That's 11.6. Yeah, so that's what we were looking for. A turns out to be minus 11.6. That's our final answer. Okay, we had to show that. Make sense? That part was, again, not that complicated. We equated the perpendicular forces. We equated the perpendicular forces, and along the plane, we applied Newton's second law of motion. All right. Okay, let's move on to the next part now. It says, find the time for which the particles are in motion before they collide. Time for which the particles are in motion before they collide with each other. Okay, now how do we do that? We know the acceleration for Q now. The distance between them is 6.4. So now it's a scenario that looks like this. We've got P here, and we've got Q here. The distance between them is 6.4. P is moving down the plane, and Q is moving up the plane. For Q, we can say the upwards direction is positive. For P, we can say the downward direction is positive. What do we know about both the particles? About P. P was released from west. So its initial velocity is 0. And what else? Do we know anything else about P? No. What about Q? About Q, we know the initial velocity at which it was projected. It was projected at an initial velocity of 10. That's the initial velocity. We know the acceleration for this. That's minus 11.6. And that's all the information that we've got. Now we think about the other pieces of information that are common between them. What's common between P and Q? Is there anything that's common? They both started at the same time. They both started simultaneously. So until they collide, they would take the same time from the starting point. They started at the same time at the point of collision as well. It would be the same time instant for both of them. So the time they take, that's going to be common. So when we have multiple particles, we try to connect them using what is common between them. So if time taken by P is equal to T, we can say the time taken by Q is also going to be T. What else can we connect between them? We know the distance between them was 6.4. Distance between them was 6.4, initial distance. So let's suppose the collision happens somewhere here. Let's call this point X. That's where collision happens. P would have traveled some distance down the plane. Let's call that SP. Q would have traveled some distance up the plane. Let's call that SQ. Their sum has to equal 6.4. Sum of their displacements that is supposed to be equal to 6.4. That's another thing that we can connect them by. So that's what we can use. We can say SP plus SQ, that should equal 6.4. That's an equation that we can make out of that. But the problem is we still have one thing missing for P. We only have two things here and one thing here. That's 3. We need 4 things to be able to make an equation. What else can we use for P? Acceleration or final velocity? Final velocity we don't know anything about, but can we find acceleration somehow? P is also on that same surface. What are the forces acting on P? Let's think about that. The mass of P was m. So what forces are acting on P? There is weight of P that acts vertically downwards. That's one force. That's 10 times m. There is going to be normal reaction. There's normal reaction that acts in this direction. What else? There is friction. Where does friction act? Friction in case of P acts in the upwards direction, is going to oppose the motion. These are the forces acting on P. Can we find acceleration using this? We know that the angle at the bottom, this was alpha. If this is alpha, we know this angle here is also going to be alpha. So the component acting along the surface, that's going to be 10m sine alpha. And the other component, that's going to be 10m cos alpha. Right? Let's apply Newton's second law of motion on P now. Opposite forces are going to be equal to each other. R is going to be equal to 10m cos alpha. They're going to be equal to each other. And along the surface, we can apply Newton's second law of motion. We've got friction there. We've got 10m sine alpha. And is that it? These are the only 2 forces that we've got acting along the motion, along the plane. All right. So now using these 2 things, what we can do is we can find the acceleration for P as well. Let's do that. I'm going to do that calculation here. What I want to do is I'll take it to the next page. Let's do the calculation for P. R is going to be equal to 10m cos alpha, right? And along the plane, forward direction is this, right? It's moving down the plane. 10m sine alpha, 10m sine alpha minus the backward force, which is friction. That should equal mass into acceleration. Mass is m into acceleration. Mass is m, right? Yeah, for P, the mass is m. This is what we end up getting for P. All right. Now let's solve this equation to find the value for A. We've got 10m sine alpha. The value for sine alpha was 0.8 minus friction. Friction is mu times r. Mu is the same for both of them. Mu was 0.6. So we can say that 0.6 into r. We write it like this first. That equals mass into acceleration. That becomes 8m minus mu, which was 0.6 into r, which is 10m into cos of alpha. Cos alpha, that is 0.6. That equals mass into acceleration. That will give you 8m minus 6 into 0.6. We found that above as well, I think. Did we? No, that was different. What do we get from this? 6 into 0.6. That's 3.6, I think. 3.6 times m equals mass into acceleration. M gets cancelled, and we get an acceleration of 4.4 from this. Is that okay? Is that the value of acceleration that we get? 4.4? Yeah. All right. So that's the value of acceleration. Now that's the acceleration of the particle P. So now for both the particles, we've got enough information. We know initial velocity, time, and acceleration for P. We know initial velocity, time, and acceleration for Q as well. Let's use this equation now. The sum of their displacements, that is supposed to be equal to 6.4. We get an equation from this. SP, what would that be? Ut plus half at square. That's the equation that I'm going to use here. S equals ut plus half at square. Right? What is SP going to be? U is 0 into time, that is t, plus 1 over 2 into a, which is 4.4 into t squared plus 10 into t plus half into a, which is minus 11.6 into t squared. That equals 6.4. Now we can solve this equation, see what we get from this. 2.2 t squared plus 10t minus 5.8 times t squared equals 6.4. And we get a quadratic equation from this. Okay, after all this, they want us to solve a quadratic. This is minus 3.6 t squared plus 10t minus 6.4 equal to 0. That's the equation that we're getting. Just put this in the quadratic formula, write down the answers. See what that turns out to be. T equals minus 10 plus minus square root of plus 10 whole squared minus 4 into minus 3.6 into minus 6.4 whole divided by 2 times a. That's 2 into minus 3.6. And that will give you the values for time. You'll get two values of time. One will be positive, the other most likely will be negative. You can see what they turn out to be. What are the values of t that we get? Values of t. 1.78, that's one value. And 1. 1.78 and 1. Okay. We're getting two positive values. Have we missed something here? 20m cos alpha, 20m sin alpha. Can you spot any careless error somewhere? Time for which the particles are in motion before they collide. Okay, so m started from there at rest, and coefficient of friction was 0.6. On the right side, I wrote 6.4, right? 6.4 was the total distance. Yes. P was released from rest and Q was projected up at a speed of 10 meters per second. Okay. U0, let's just check the values quickly. P started from rest, right? Okay, that's 0. Time taken by T and P and Q, that's going to be the same because they started at the same time and then they are colliding. So that has to be the same. Yes. What else? Q was projected upwards. Q was projected upwards and U is equal to 10. That's also fine. A is minus 11.6 and PQ is T. Ten M was the weight. That is fine. Okay, so Q was projected up the plane and Q was projected up the plane and P was going down. We took the initial velocity as 10 for this, acceleration this, time this. And then we said that their displacements should add up to 6.4. 10m into cos alpha. That's also fine. That's the value for R. Cos alpha, what was that? Cos alpha was 0.6. Mu is also 0.6. Plus mass into acceleration. The value for acceleration that we get is 4.4. Okay, so that might be the problem. Wow, how would you figure this out in the exam? Okay, so we did it the normal way, and it turned out that we were getting two values of time from here, one this and the other this. Okay, we were getting two values of time here. Now, we can't have both possible answers. That means there could be something that is off here. And what I realize now is when Q is going upwards, since its acceleration is so small, it can change its direction at some point before it collides. Before it collides, it can change the direction. And if it changes direction, its acceleration is going to be different. Its acceleration is going to become different. Why? Because when it was moving upwards, friction was opposing that motion. And the value of acceleration that we got at that point was minus 11.6. But when it starts moving downwards, if it does, what happens is friction is going to act in the upwards direction, and its acceleration is going to change because of that. Its acceleration is going to change. So we have to figure out if the collision happens before it changes direction or not. Now, can we figure out at what point it changes direction if it does before collision? Let's try to figure that out and see at what point it changes direction. So the acceleration of P, that's fine. This is okay. But now if Q is going upwards, if Q is going up the plane, we know its initial velocity is 10, its acceleration is this. Can we find the time taken? Can you find the time taken until its velocity becomes 0? So let's say before collision, it comes to instantaneous rest at some point. Can we find that point somehow? In that case, final velocity would be 0. Let's find this value for time. V equals u plus at. And that becomes 0 equals 10 minus 11.6 into t. What's the value of time that we get from this? So what's the value of time that we get from this? 11.6. 10 over 11.6, which is 25 over 29. Okay, so this is the time at which its velocity becomes 0. So it comes to rest and it changes direction. It starts moving downwards. Now, the two values of time that you've got from here, the two values of time that you've got from here, these are both greater than that number. These are both greater than 25 over 29. That means before the collision happens, before any collision can happen, the particle Q is actually changing its direction. It's changing its direction. Q has started coming down already. Okay, so that explains the threshold now. For this question, at least, there's no way you can figure this out in the exam without having a lot of time, which you would not have in this paper anyway. Okay, so let me repeat what I'm saying now. What's happening is Q was going upwards, P was going downwards. Before they could collide, Q has actually started returning towards the ground. That's what is happening. Now, because of that, we have to consider the change in direction, and because of that, the acceleration is also going to change. So we have to consider two parts of this journey now. One part in which Q is moving upwards. How much time does it take? It takes 25 over 29 seconds. That's the time that it takes. 25 over 29 seconds. Okay. Now, in that time interval, how much? Oh, just give me a second. I'll be back. Okay. All right. So you're saying the marking scheme is giving special case marks, 4 marks for students who did not consider that the direction was changing. Okay. All right. Okay, so we've got this. T equals 25 or 29. That's the time that we're getting. Now, it's that time where my kids are storming into the room now. Okay, just give me a minute. I'll be back. Let me check again. Okay, sorry about that. Where were we? Hmm. Okay, so we said that the direction of Q is changing. Direction of Q is changing at this time instant. Okay, so let's see what happens until that point now. Until that point when the direction of Q changes. So we have to break this journey down into two parts now. Have to break it down. It's actually that type of question in which Cambridge realizes after making the paper and after actually making the marking scheme that they've done some blunder while making this paper, because there's no way you can do this in an exam. Nobody would have gotten 50 marks in this because it's just not possible to do it, to figure this out in the exam. It's a very unfair question. Time t equals 25 or 29. Okay. So what we do now is we break this journey into two parts. We consider the first this many seconds, see what happens in that part of the journey. For P and Q, both of them, how much distance that does P travels in this time? Let's figure that out, because we need to know at what point they are at this in this case. once Q at the instant, Q changes its direction. We need to figure that point out. So let's find the displacement for P in that time. Initial velocity was 0. So S equals ut plus half at squared. That's what I'm using. S equals u 0 into t, that's 25 over 29. That will just be 0 plus half into a, that's 4.4 into time, that's 25 over 29 whole squared. And that will give us the displacement of P at the instant when Q changes its direction. What does this turn out to be? Can somebody do this for me? SP, what's this value? 1.635. Okay, so 1.635. What's that telling us is at the point that Q changes direction, this is the displacement of P from its initial position. What about the displacement of Q until this point? Let's figure that out as well. SQ until this point. What would that be? U is 10 into time, which is 25 over 29, plus half into A, which is minus 11.6 into T squared, that's 25 over 29 whole squared. You can see what that turns out to be. 1.63, 4.31. Okay, it's 4.31. Can I have more significant figures? 4.3, and then after that? What about after this? 4.3103. Okay, 4.3103. All right, thank you. 4.3103. That's the displacement of P, displacement of Q when it changes direction. So now what has happened is, in this journey, the distance between P and Q, the total distance initially, that was 6.4. Now P has traveled some distance in the downward direction, and that's 1.635 meters. Q has traveled some distance in the upwards direction, and that is 4.3103. How much are they still away from each other at this point now? Can we figure that out? That will be 6.4 minus this. 6.4 minus 1.635. Minus 4.3103. What do we get from this? What's this value? 0.4547. Okay, thank you. 0.4547. This is the distance between them at the point Q changes direction. Distance between particles when Q changes direction. Q changes direction. This is the distance that we put. Okay. Now we have to consider the next part of the journey after this. When Q changes direction. So once Q changes direction, what happens after that? We'll have to do that in the additional page now. So once Q changes direction, now we've got a situation that looks like this. After that point now, we can say the distance between P and Q, that is 0.4547. Now P is moving downwards. Q is also moving downwards. Both of them are moving downwards. All right, both of them are moving downwards. So what do we know about both of them now at this point? From this point onward, do we know the velocity of P at this point? We don't. We'll have to find that as well. Could we just do that from the beginning then to make it simpler? You think about it, if I do that from the beginning, I would have this distance and also the previous distance. We would still need that point. Okay, so what we also need to do now is we need to find the speed of P at this instant when it changes direction. What would that be? Because that will be the initial speed for this part of the journey now. So we don't know the initial speed. We have to find that. And we know the acceleration. We found that earlier. Acceleration was 4.4. What else? We know that the time is common between them from this point onward as well. And the displacement is going to be like this. If for them to catch up with each other, whatever, so for example, if they catch up here at this point, the distance traveled by SP, that is going to be equal to distance traveled by Q, that's SQ, plus this, which is 0.4547. So we can connect them like this eventually. But before that, we need the initial velocity for P as well. For Q, we have this information. For Q, we know that the initial velocity now from this point onward, that would be 0, right? Because it returned at that point, it changed its direction. So initial velocity would be 0 at this point. We know the acceleration as well. So when Q starts moving downwards, its acceleration is going to be the same as the acceleration for P, because both of them are moving downward. Both of them have the same coefficient of friction. So the acceleration is going to be the same as well. So if it was 4.4 for P, it will be the same for Q as well. You can evaluate that again as well. Think about it. In this equation, even if you were to replace 10 with 20 here, so M with 2M, so if M gets replaced with 2M, that does not change anything, right? If we replace M with 2M here, nothing changes, everything gets cancelled, and you get the same value for acceleration. So acceleration for Q, after it has changed its direction, is also going to be the same. It's also going to be 4.4. The time is also common. So the only thing that we want to find out now is the initial velocity for P at the point Q changed its direction. How do you find that? That will be the final velocity in this part of the journey. Let's figure that out. Let's see what that is. Vp equals U. Earlier initial velocity, that was 0, plus A, which was 4.4, times the time taken. Time taken was 25 over 29. What does that give us? That's the velocity of P at the instant when Q changed its direction. What's this? What is this value? 4.4 into 25 over 29. Anyone? 3.793. Okay. 3.793. This is the velocity of P at the point Q changed its direction. So that becomes the initial velocity here. That's 3.793. 3.793. And now we do something like this, that the displacement for P minus the displacement of Q, that will be equal to this, or displacement of P equals displacement of Q plus 0.4547. Let's see what that turns out to be. SP, what would that value be? U into T, U is 3.793, times T, which is T, plus half into A, which is 4.4, into T squared. That equals 0T plus half into 4.4 into T squared plus 0.4547. What do we get from this? These two get cancelled, thankfully. And we don't have to solve a quadratic here. And that just leaves us with 0.4547 divided by 3.793. And that's giving me 0.1199. That's the time taken. That's the time taken after Q changes its direction. So what's the total time taken then? 25 over 29 seconds had passed already earlier. At the point when Q changed its direction until the point when Q changed its direction, plus this 0.1199, and that will give you the result. You can see what that is. That's 0.982. That's the time that I'm getting from this 9819. That's 982. That's the total time taken. Does that make sense? It's very complicated. Quite an unfair question. Quite an unfair question. But that's what you would do. Okay. So that explains the threshold. People would have not been able to do this. And then the next part, which does not seem to be as difficult, that would have also been left because of that. So you lose like 7-8 marks there right away. And then you have the rest of the paper as well. Okay. Abdul Hadi, I'll share the recording right away. I'm in a lot of pressure right now from my kids. They're about to sleep and they want ice cream right now. And it's getting extremely late. So we need to be quick. I'll share the recording right away, okay? The particles coalesce on impact. The particles coalesce on impact. Find the speed of the combined particle immediately after the impact. Okay. They coalesce on impact. All right. So what do we know about them? We have to again find the velocity at the time they collide with each other. So we've got this information. We've got this information here for this part of the journey. Let's use this to find their velocities at the time they collide with each other. Okay. Can we find their final velocities from here? Final velocity of P, final velocity of Q. Let's see what they turn out to be. Initial velocity is 3.793 plus A, which is 4.4 into T. What was the value for T? Did we find that here? 0.1199. 0.1199 from the previous part. This plus 4.4 into 0.1199, that will give us the velocity of P at the time of their collision. And similarly, here we have 0 plus 4.4 into 0.1199. That will give us the velocity of Q at the point of collision. What do we get from this? Velocity of P at the time of collision, velocity of Q at the time of collision. What do we get? 4.3205, that's the first one. What about the other one? Zero 0.5275. Thank you. So these are their velocities just before collision. So can we find the velocity of the combined particle now? Mass of P, that was m, right? Mass of P was m. So it becomes momentum before collision, which is m into 4.3205 plus 2m into 0.5275. That should equal momentum after collision. M plus 2m, that's 3m times velocity of the combined particle. Let's call that particle C. That's VC. That's what we're looking for. M and M, they will get cancelled, and we would get the velocity of the combined particle. You can see what that turns out to be. 4.3205 plus 2 into 0.5275 divided by 3, and that turns out to be 1.79. That's the velocity of the combined particle that we were looking for. See, the last part was fairly straightforward, but you cannot do this unless you've done the previous part. So because of that, you lose these marks as well if you were in this exam. Okay, so that was this paper. This question was extremely difficult, part B of this. And then At the time it came, this part 6b was also difficult. So that explains the threshold. That's what you do here. That's it for today. I will see you again in the next session. Now, tomorrow we have our M1 workshop, inshallah, from 5 p.m. or 5:15 p.m. onward, sometime around that time. Okay. So we will have uh, a revision workshop around 5:15 p.m. tomorrow, inshallah. And then the next week we'll have classes on Monday and Tuesday. On Monday, we do difficult questions from the June 2022 papers, inshallah. And then Tuesday will be an open session in which you can, ask any questions that you might have. All right, so that's it. I'll see you again in the next session then. Allah Hafiz. Take care. Okay, Allah Hafiz.